Good morning, everyone, and welcome to Engineering Tomorrow's Optimizing Networks special lab event. We're so thrilled to have you guys with us today and hope you're ready to have some fun coding. We have an amazing keynote speaker we can't wait for you to hear from, as well as a pretty amazing engineer to lead the day. So I'm excited to hand it over to her, Mrs. Joanna Cottle.
Hey, good morning, everybody. Hello. I'm really excited to be with you today to talk about a relatively new area of mathematics and programming that is being applied to some of the most complex problems out there. Thank you, Jillian, for the nice introduction. My name's Joanna Caudle, and I have a background in mechanical engineering and physics. And so thinking about ways to model the natural world has been something that really sparked my interest in physics and engineering right from the start. Um, I thought we could start today by asking you to think about a video that you have watched recently that you know went viral. Um, Something that everybody's talking about. Have you ever wondered what makes a video go viral or a meme go viral? What's happening behind the scenes? Today, that's what we're going to be looking at and getting a closer look at what goes on and how algorithms that are used by Google and TikTok and other social media sites um, spread a popular video or a picture or a search term. So I'm just going to share my screen, and I thought I would start by a picture that went viral on my social media. And I'm hoping you're seeing, are you seeing my screen now, Jillian? Yes, we're good. Okay.
Good to go.
So here we go. Who has seen this cute little guy? Everybody say, "Oh, this is Mu Deng." I'm sure you already know that. He showed up on a lot of social media feeds. Lots of people were making memes about him, and I'm wondering what is it about him that caused pictures of this cute little hippopotamus to spread so fast? Does anybody have any ideas? Feel free to write it in the chat if you want. If you've got your devices open, I'd love to know. But I mean, for me, he's feisty, he's cute, he's got a lot of personality. It seems like everybody could identify with him. And then another one that I thought might have shown up on your social media feed. I didn't hear about him until he was on Saturday Night Live, but how about the Rizzler? Does he look familiar to you? I made a very poor attempt at making the Riz face, but this is another little guy that was all over the internet for a little while. So what causes these cute pictures, these funny personalities to spread so quickly? Let's start to look at that. So when you think about what does it mean to go viral, how does that happen? Well, by definition, going viral means to create content that is shared exponentially on the internet. I bet a lot of you probably could think about that. And that word viral comes from the word virus, which we all know is a medical term to talk about an infectious agent that can infect a lot of organisms. So it's also a computer term. It's used on the internet. And so just like a virus can spread, these popular videos, these memes can spread really, really quickly and can feel like a virus. So let's think about that. Part of the answer about why things spread so quickly is based on the data that's being collected. If you imagine that you watched a video of Mu Dang playing around with his caretaker and you watched that all the way through, that was a piece of data collected about your viewing habits. If you shared that video with a friend or you made your own meme out of that video, that's another piece of data. And what happens is companies like TikTok are using algorithms that analyze that data and help it to spread quickly via the internet. The way they do that is through um, a use of networks, and the kind of the study of that is called network theory. So I'm going to show you a quick snippet of a video that goes into a little more detail about this, and then we'll come back and we'll kind of talk about what are some of the key points we've heard. So here we go. Can you give me a thumbs up if you're seeing the video now? Are you seeing a
Yes.
TED-Ed video? Yeah, great. Okay, here we go.
But what are networks? Everyone knows about their social network, but there are all different kinds of networks you probably haven't thought about. Networks are collections of links which combine by specific rules and behave as if they're alive. We say that networks are alive because they are in constant change. Over time, the connections within a network migrate and concentrate in new places, forming evolving structures. How the evolution and concentration of constantly changing connections occurs is the subject of a whole discipline called network theory. We can think of networks as neighborhoods. Neighborhoods are defined by maps. A Google map demonstrates the relationship between locations in exactly the same fashion a network connects hubs and nodes, using streets as links to connect neighborhoods. The reason a network can expand and evolve so quickly is based upon a mathematical concept called power functions. A power function is a mathematical amplification mechanism which over specific and very small ranges accelerates changes logarithmically. That is, a very small change in one parameter produces a huge change in another over a very specific range of values. An example of how network structure emerges is the algorithm used by Google. As the number of links around a search term, say friends, increases, connections begin to form among millions of different searches using the term friend. What Google has cleverly accomplished is a real-time mathematical model for how to predict the emergence of growing connections among billions of search terms. The algorithm Google derived collects the number of references to any search object. As references to a search object increase, the number of links also increases, creating a node. As the node increases in size, it eventually becomes a hub, which links to many nodes. Networks will continue to emerge as new ways of connecting and creating neighborhoods are defined.
Okay, so that went, I slowed that down just a little bit because it was a lot of information at once, but let's break that down. So networks are a collection of links that combine by specific rules and behave as if they're alive because they're constantly evolving and changing. Networks are neighborhoods defined by a map or a graph where paths in the network are connected by nodes. We also heard something about how networks can spread information very rapidly because they use a power function. And you guys have probably heard of a power function before, like x squared or x cubed. So you know for a small value of x, when you square it or cubed it, it can get really big quickly. And that's the same case for a power function used in network theory. And we're going to study that in a little bit more. And the last term I wanted you to think about was when networks grow and change and we get a lot of data around one node, that node becomes a hub. And then that hub can be used to connect to many other networks. So there's just a bit of a background. And now let's talk about how are we going to practice that and look a little closer at that today. So what we're going to be doing is I'm going to give you a little bit more description about what networks are and about the mathematics behind the algorithms that are used in networks, which use the mathematics, a theory called graph theory. And then we're going to look at a classic problem, the traveling salesman problem. And I'm hoping that you're going to be able to work along with me as we work through this problem. But this is a classic problem, and it's a great way to have an introduction to networks. And then you're going to have a chance to code using block coding, some simple block coding, to code a virtual drone to follow the route that you come up with for your traveling salesman problem. And here's kind of the schedule for the day. If I'm gonna be talking to you for a little while longer and helping you through some of the initial parts of this challenge day. And then you're going to have about an hour to work on the challenge yourself. You'll be in breakout rooms, and that will help you. You'll have helpers there should you have any questions. And then I'm going to be rejoining you at 11:30, and I'm going to have with me 2 current engineering college students that will be available for you to ask any questions about college, about engineering, about our careers. And then I'm really super excited to be able to talk with you and joined by Rakib Jamil. He's our keynote speaker today, and he is a data scientist who is working his dream job with the WNBA. And so he's going to come and share a bit about his journey to computer science, and then you'll have a chance to ask any questions and hear his inspiring story. So we've got a full day ahead of us, a full packed morning ahead of us, and I'm excited to get started. As with any engineering challenge with Engineering Tomorrow, they are always developed by professional engineers and current engineering college students. And this challenge was developed by my friend Edgar Martinez, and he collaborated with 3 students, Kira, Julian, and Gigi. And you can see there from the slide that they had all different kinds of engineering backgrounds. So one thing I love about working at Engineering Tomorrow is the chance to collaborate with so many different kinds of people who have so many different specialties. Okay, so let's get going on a little bit more introduction into what is the analysis used in network theory. So you've learned that a network is a group of interconnected things. And we know that they behave by specific rules and behave as if they're alive because they can constantly change and evolve. So they have so many applications in the real world, not just in the computer realm, but also you could think about our brains being a network where the neurons in our brain are sending signals to each other. You could think about Amazon and FedEx trying to come up with the best routes for their drivers to take or their shipments to travel along. And even perhaps Alexa and Siri, how they can learn new things. All of that is through network theory. As I mentioned, the math that's used is graph theory. And we're going to learn a little bit about how graph theory works, very introductory level. This is a math that really has only been used a lot in probably the last couple of decades. So it's kind of a new way of analyzing things, but that's what scientists and engineers do. They come up with better ways to analyze and create models to better models to come up with solutions to problems. So we've talked about what are real world applications that can be used. I've talked about scheduling deliveries, airline route planning. But what about things like the spread of infectious disease and predicting how quickly a virus might spread? We've been hearing a little bit about bird flu. I'm sure scientists are looking at that to make sure and follow closely where it's spreading to predict how to contain it. Google Maps would be another great application that uses network theory. And again, we've talked about our brain where neurons connect to one another, and then these groups of neurons create complicated networks that send signals passing information through our brain. So lots of different ways that network theory can be used to solve complex problems. But today we're going to be solving a problem, or we're going to be coming up with an approximate solution to a problem that's a classic one. And it's actually a problem that currently doesn't have a specific mathematical solution. And that's why we're using these various techniques to approximate the best solution. And so to give you a window into that, we're going to do a couple of trials of the traveling salesman problem. So it's kind of a straightforward problem. If you had 9 cities, if you look at this map, it's got 9 cities highlighted on it. What would be the shortest path to fly to each of these cities exactly one time? How could you figure out, would there be an optimum place to start? Would there be a hub that would be great to use for routing? These are all the kinds of questions that are associated with the traveling salesman problem. So to give you an introduction to it, we're first going to do a simulation of the traveling salesman problem, and then you're going to have a chance to break that down in a little bit more detail with a calculator that we've developed for you. So let's get started. So which city should we start from? To do this, and I encourage you to follow along with me, we're going to use this simulator. So if you, in your workbook, I've got the worksheet up here. And if you can see, if you scroll down, you've got this link that you can use to start this process. And if you click on that link, it's going to open up this simulator here, the traveling salesman problem. And when you get there, you're going to create a new game. And here you're going to see different countries you can pick. So maybe I'll pick Germany. And then you're going to look at a number of cities. And so if we go back to my worksheet here, you're going to see that you're going to start with 3 cities. I'll go ahead and do one where we start with 5 cities to help you see how it works. So you just slide the slider along until we get to 5 cities, and then you hit start game. And it says, don't forget, visit every city only one time. So hopefully you can see this on my screen, but and on yours. Here I've got the country of Germany and little blue dots representing different cities. And so all you do is you pick where you start. So maybe I will start here. And I'm going to go up here and I'm just connecting dots. And here to Kiel, down here to Moors, and I'm just clicking on a dot once I get there, Konstanz, and then back to Siegen. Okay, so I've got my solution, and you can see there's probably, just going around the edges is probably a good way to go. The length of my tour is 1,656.7 kilometers. Is that the shortest route? Well, what you do is you show your solution, and it'll say, once you do this, you can't go back. So just go change tab, and you can see that my tour is not optimal. Apparently, there's a faster way I could do this, but I'm pretty close. And so what you'll do in your worksheet is you will fill out the table that shows your tour and then the optimal tour. And you're going to do that for a number of cities. Once you do that, once you record your data, you can click OK. And then you just go back to the tab and create a new game. And now you can increase the number of cities. You know, I could go up to 10 or 12 or whatever. And start the game again. And now you can see you've got a few more cities. It gets a little harder. It quickly gets quite hard to figure out just by looking at the map what would be the optimum. So that's part 1. It's going to give you a little taste of the traveling salesman problem. And we're asking you to do that for a few different trials so you can kind of see, is there a trick to it? Is there a way to try to figure out the optimal solution? Is there a good city to start at? So this will just give you a little taste of what the kind of analysis that you're going to be doing. And then after that, you'll have time to come back to that, but let's move on and let me show you a little bit more about the next part of the traveling salesman problem. This one is specifically in the United States and involves 9 cities. So let's take a look at it. So I've told you a little bit about network theory and that the mathematics of used to analyze networks is graph theory. And I've talked to you a little bit about how this is a relatively new field of mathematics. And it's really the first textbook wasn't even published for it until the 1960s. So I know that sounds old to you, but that's relatively new for classic mathematics. So let's find out a little bit more about what graph theory involves. So I've got a short video just to show you. Let's see if I can play it from here.
Graph theory is not about plotting my hot dog consumption over time. I don't know who told you that. It's about mapping the relationships between objects. And the 2 main parts are nodes, which are the elements to be connected, and edges, which are the lines that connect them. Here's why it matters in real life. You've got 3 houses, A, B, and C. All of them need to be connected to utilities, water, gas, and electric. What's the most efficient way to create that network to service all 3 houses? Graph theory. It's actually impossible to solve this one without crossing lines. Your mail carrier figuring out their most efficient route. Graph theory. Building roads that make sense. Graph theory. Social networks figuring out who to show your grandma's dog to when he gets back from the groomers. Graph theory. You being shown this short right now, graph theory. You are a node. A node. Okay, bye.
Okay, so let's take a look at that. We're going to be using graph theory, a simple form of it, to solve this problem. So we're going to be modeling the traveling salesman problem using a graph. We're calling it an undirected graph or weighted graph because it won't matter which direction we travel in. We could go clockwise through our cities or counterclockwise through our cities. The graphs, the cities on the graph are vertices, or those nodes we were hearing about in the video. And the paths between the cities are called edges. So what we're trying to do essentially is come up with the minimal amount of distance that a person would have to travel to visit all these cities. So let's look at this a little further. If you remember, I talked to you a little bit about in the beginning how networks, things can go viral and spread very quickly because of that power theory. And so let's look at that. We've already seen that this traveling salesman problem becomes very complex very quickly as soon as you add more cities. So if you look at the map here in the picture, you can see that it's the map with the 9 cities located. One possible solution could be kind of to go around all the edges of the map. But actually, when we think about graph theory, if we take away the map, it doesn't really matter what those nodes are. What we really have is a graph with the nodes or vertices and the edges being the distances between the points. And it's not really relevant which direction I travel in. It's really just the graph. So that's the starting point to think about the mathematics behind graph theory. So now let's look at some of what happens and how quickly it becomes complex. So for 3 nodes, you can see there's only one path you can take to get between these 3 nodes. It doesn't matter whether you go clockwise or counterclockwise around it. When I get to 4 nodes, now I've got 3 different paths I can take. I can go around the edges or I can cross through the middle. When I get to 5 paths, you can probably imagine it's going to start adding up. And it adds up quickly using a power function. And that power function is a factorial function. And you can see it up there on the upper right. So the power function that relates to traveling salesman problem is n minus 1 factorial divided by 2. So for 5 nodes, you can see I'm going to have 5 minus 1 factorial, or 5 times 4, 4 times 3 times 2 times 1, that quantity divided by 2. So I'm going to have 12 nodes, 12 paths. And if you can see as you go up, look how quickly it goes up. When I have 9 nodes, over 20,000 paths. When I have 12, 19, almost 20 million paths. So that starts to give you a picture of how quickly networks can spread, information can spread through networks. So now let's look at this problem. This is the second part of our traveling salesman problem. So you got these 9 cities and you're trying to find the minimal distance a traveling salesperson would need to travel to hit all those cities exactly once. And so what we've done for you this time is we've created a spreadsheet. So if you go back to your worksheet, I'm going to run through this. We're in the traveling salesman part of it. And I want you to click on this link, make a copy of this spreadsheet. So if I click on that, it's going to open up this spreadsheet. And I'm going to make a copy of it. And the first part that you're going to do for this problem is we've given you the map and we've overlaid a graph over it. And what we'd like you to do is put in the X and Y coordinates for each of those cities. That's going to allow the spreadsheet to do the calculations for you and save you a whole lot of time. So let's say I want to put in the coordinates for LA. Well, LA's at about 1.5 and 7. So I'm going to put that in 1.5 and 7. And I won't put them all in because you can do that in a minute. But you can see when I do that, it starts to calculate the distances between LA and Seattle, between Denver and LA, etc., all the way through. And then all that is going to be done for you once you complete this table. And then if you scroll down from what I'd like you to do is look at that, and you'll start to see some distances. And it might help you figure out what path would I want to take. You could look for where the minimum distances are. And then what we've done is we've created a drop-down list for you to create a route. So just for this example, I'm going to start at city A, which is Seattle, and go to city B, which is LA. And you can see it starts to calculate the distance between those cities, which it's pulling from up here, 904, 904, and it's also plotting the route for you. So just to reiterate, step 1, fill out the table with the coordinates from the X and Y coordinates. Step 2 basically is done for you, but step 2 would be look at this table and see if you can start picking out the minimum distances, and then think about how you would fly across the country if you were a salesperson visiting different sites. Enter the letters of the route you want to take and look at the distance, the total distance that gets calculated there. This is what you're going to put in your spreadsheet, your worksheet when you're done. You're going to try it a few times, and when you like what you've got, you'll enter the cities here and the total miles and the fuel, which is just 0.025 times the number of miles that you have. So Challenge Prep and others, I encourage you to compare with your classmates, see who can get the lowest total miles traveled for the traveling salesman, who can come up with the best solution by having the lowest mileage and visiting every city one time only. Once you've come up with the path that you like, then you're going to have a chance to code a drone to fly to all of those to fly to all of those places. And so this is the last part of it. Take a big stretch, and I'm just going to show you one more application that you'll be using to finish the challenge today. And that is, we're going to use a program called MBlock. And so if you go back to the worksheet, I'm just going to have you scroll down a little bit further, and you're going to see there's a website here. Go to this link, and it's going to open this site called MBlock. And with MBlock, you can use Python coding or you can use block coding. So if you scroll down, you're going to click on the button Code with Blocks. And that's going to open this window. Another thing that you need to do so that you have a drone to work with is to click on this link here. And that's going to open these files. And what I'd like you to do is just download those onto your device. So I clicked here in step 3, and I'd like to download those to my device, because what I'm going to do is go over here. Once I have MBlock open and I'm coding with blocks, the first thing you're going to do is go up to File, and then open from your computer. And might go to your downloads folder, but I have mine in my desktop. You're going to click on this drone simulator and open it up. Might take a minute. Okay, and so now what you've got is the map of the cities kind of on a graph paper, and you've got a drone as your sprite that you can move around. And the way that you can start any program, the way you start is always with a block called, it's in the events category, and it has a green flag. I guess it's already in there. So we can start on that. And then we're going to want to use our motion blocks. And the one that I like to use is glide to a certain position. So you can click that there. And this says, take 1 second to glide to a certain spot. So if I want my drone to start here, I can move the drone here. And you'll see that it changes the X and Y coordinates down here for my sprite. And so if I plug those in, 26 for X and -96 for Y, when I click play, I could move this somewhere else. When I click the green flag, it flies to that point. So when you figure out the path that you want to take, you can program your drone, and you can see that there's other things you could use. You could have it move according to a keystroke, but the glide function is a good one to get you started. So those are our 3 activities today. Programming the drone. And if you really want to get into it, you could think about the distance each path has taken by saying that each of the blocks in the map of your city is worth 20 steps. And so you could see if you could come up with a minimum distance as well. So I want to thank you so much. I know I've thrown a lot of information at you, but you're going to have helpers in our breakout room today and support along the way. And I just hope you have fun with it and learn more about network theory. So thank you very much. And I look forward to seeing you back here at about 11:30.
Thank you so much, Joanna. That was a fantastic introduction. You still have that teacher magic on you. It shows. Thank you so much.
I don't have the Riz face, so.
No, I think yours could go viral. You guys, I think you're ready. Joanna has prepared you. We will go ahead and open up the breakout rooms for you to get to work. We will meet you back here at 11:30. There will be ET staff and 2 amazing college mentors in the breakout room with you to assist. And go ahead, have fun, work hard, and we'll see you back here at 11:30. Thanks.